going to be variational calculus review and so forth. So we're now doing Lagrangians. So Lagrangian mechanics. And what we have so far, we have a couple of example Lagrangians. So L equals T minus U. And the projectile motion mx dot squared, I'll write it out this way. So that's projectile motion in 2 dimensions. There's kinetic energy minus mgy. And we took the Euler-Lagrange equations and we found that they gave us what we're accustomed to seeing. The other example was for plane polar coordinates for the central force Lagrange. And so here we had a half m r dot squared f m r squared v dot squared minus negative alpha over r. Did I write it this way or did I put a u of r before in your notes? I'm going to put u of r just minus u of r. So that would be your central force. And central force with new potential would have been negative alpha over r. But, so the advantage of this whole thing, I'll write here, S equals integral L dt and delta S equals 0. This being that whole process coming up with the variational derivative, that gives us d over dt dl d. What did I have so far? R dot minus dl dr equals 0. 3 equations at a time, and this was Newton's law. Euler-Lagrange equation that's actually turned into Newton's law. But with these examples, we already see something interesting going on because we can do problems in different coordinate systems. These here, this was Cartesian, but because this is a scalar, right? Energy minus potential, kinetic minus potential. This is a scalar, we can express it in any coordinate system we want, and then we'll automatically get the equations of motion. So our next topic is called generalized coordinates. Generalized coordinates, that's some new terminology. But plane polar are, for example, an example of what we're talking about. So generalized coordinates, we're going to call that a set, we're going to name that Q, a set of Qi that are independent, or a set of Qi that are independent, important property, and they describe the position of our mechanical system. Describe the position of our mechanical system. And what we then want to do is express our Lagrangian in terms of those coordinates, and then we'll have the full power of the principle of least action at our disposal. So we we need these generalized coordinates. Like I said, this is already one example of it. So I will just go in here and just write down what some of our examples are. And the first example, I'm going to just say projectile motion, so Cartesian coordinates. Cartesian coordinates, x, y, z. That's fine, okay? But here's a counterexample. Cartesian coordinates x, y, z if where motion is restricted to a sphere. You know, suppose you have a sphere and you have a bead rolling around inside that sphere, and it's in contact with the sphere. So where motion is restricted to a sphere, spherical surface. Now, this is actually a counterexample. And why is that? So we've got, here we go, here's our x, y, z space. But the motion is restricted to this sphere right here. The reason this is a counterexample is those coordinates are no longer independent. X, Y, and Z vary with one another as we're moving through the sphere. So it's a counterexample. Because they're not independent, so these coordinates are not independent. A simpler example would be if you had motion in the xy plane and restricted to a hoop. Okay. Then x and y are not good coordinates because they're not independent. So that's really important. And the proof that we did of this principle actually contains the requirement that they're independent. I did the proof for multivariable systems. Okay. And so that contained the requirement of independence. So this is a counterexample, but moving along now, and in fact, rather than the sphere, I probably should have just said the hoop. Okay, sphere is true, the hoop is true. Hoop's a better example. So yeah, we'll actually continue in this vein here. So we've got x and y. X, Y, motions restricted to a hoop, say at radius capital R. So X and Y would not be independent, but R and phi are independent. And immediately we're in great shape. What we do is we take the Lagrangian that we had, the plane polar coordinates, we'll just write it out, plus 1/2 m r squared phi dot squared minus u of r and phi. And now we'll specialize this because r is equal to capital R is equal to constant. And so now we're going to turn this into 1/2 m r squared phi dot squared minus, I'm just going to write u of phi. You know, we'll have gravity in here, we'll have a bead on the wire or a pendulum or something, minus u of phi. You'll notice we took plane polar coordinates, one of them dropped out, and now it's one variable, and this is a legitimate Lagrangian. We'll take the equations of motion and everything. So this is a great example for this generalized coordinate. So moving right along here, let's go ahead and list these because we're going to have to do some work with them. So we've got the plane polar, and we'll write out the definitions. We've done this before. R cos phi, y equals r sine of phi. And the spherical polar, and x is r sine theta cos phi, r sine theta sine phi, c equals r cos theta. And so those would be the spherical polar coordinates. And we could have the cylindrical ones as well. I won't write them out explicitly, but just for the record. Now the thing with, talk about a mechanical system, what if it's a bicycle? Pedals have an angle, the wheels have an angle, the handlebar has an angle. It's a collection of interesting angles, and then the position of the bicycle on the road has a Cartesian coordinate. Right? It goes on and on. And yeah, you could construct the Lagrangian for that. One of our former physics majors was over in the engineering department. He came to me a few years ago with a colleague, and they were doing Lagrangian for a motorcycle. And it was all numerical. It was a total mess. I was glad I'm not an engineer. But yeah, these formalisms can really be extended to that kind of thing. So in particular, there will be mixed coordinate systems. I'll just give you an example, 5, 6, keep numbering here, that we'll actually be working with. I'll just give this example, numbering 7. This will be a homework problem at some point. So suppose you have a track, and it's just a y equals f of x track. And you have a bead that can slide along it, but that bead is connected with a rigid rod to a second bead, and we're going to track the mechanics of this thing as it swings along here. So then we would have to have an angle, right? That would be an independent coordinate, but y and x would not be independent because they're tied together by this thing here. So independent coordinates would be x and phi, right? And then we would try to construct the kinetic energy and the potential energy. We have a little bit of work to do. Reduce it all to Cartesian coordinates. We'll actually do this one later on. But you see really clearly, since we've got this track, we only have one coordinate x that tells us our position on the track. And then we've got this angle phi tells us the angle that thing is taking on. Good. So that's an example of mixed coordinates, right? You've got the Cartesian and you've got an angular coordinate. You've got both at the same time. Okay, so now we have these generalized coordinates and we have to get a little formalism with them. So the generalized coordinates are traditionally labeled Q. And our kinetic energy, though, we know from the Cartesian form. So we have to do a transformation. So let's call this constructing L with generalized coordinates. Generalized coordinates. That's what our task is here. So each, this gives the general form. We're going to imagine we have a Cartesian coordinate, x sub I, and it's f sub I of q1 over qn. For example, plane polar coordinates, x was r cos phi, right? So the q1 and q2 were the r and phi. Okay. And y was x sub 2 was r sine phi. So that example is clear in our mind. I'll just even put it here. In fact, I can say x sub 1 and x sub 2 is r sine. So what we have to do now is a bunch of chain rule. X sub I dot df sub I dq sub j q sub j dot j equals 1 to m. We remember the multivariable chain rule? Big summation. It's like a single variable chain rule, but then you sum over all possible ones. So watch this. This looks kind of intense. Now the kinetic energy, we have to go back to our fundamental definition, f m sub I x sub I dot squared. Summing from I equals 1 to n. What we do is the following. We take a half, sum over I, m sub I, but the x sub I dot squared, we're not just going to square this sum here. We're going to put this sum in here, df sub I dq sub j dot sum over j, and instead of squaring this expression, we're just going to rewrite it in terms of k. So df sub I dq sub k q sub k dot. So that's a legitimate way of squaring it, because we're summing over all of the i's, all of the j's here, and the same thing with changes of name. But here's the key point. We're going to take the 1/2. We can exchange the order of these summations. So I'm going to do a double sum, jk, oops, that's a j, jk, and now I have a sum of m sub I. I have df sub I dq sub j df sub I dq sub k close q sub j dot q sub k dot. We're going to make sure this all appears on the screen. Let's see what's going on here. No problem. No problem. Okay, you guys are thinking this looks bad, but it's not. So all I did was rearrange these sums, and I can do that. And you know, the summation over I, these guys are tagged I, they're derivatives. What we do is we give this thing a new name. It is A sub j k, and it's a function of all those q's. What we're going to see is anytime we do this, we just run through this explicitly. We don't have to memorize this formula at all, okay? But what we do have to realize, it has this form. It's a square matrix, because you're summing over the i's, it's tagged by j and k. It's an n by n matrix. And it's a function of the q's, because these functions f are functions of the q's. So what we're left with is another quadratic form. We're going to see a lot of quadratic forms this semester. We saw some in math methods, right? And this is another one. So we go ahead and repeat what we have here in this simpler form. So now we have for our Lagrangian, this is the generic form. J, K, A, J, K of Q, U, J, U, K, and then we would just transform the potential energy into its form with the new coordinates. So this we have to come to understand and appreciate. This is the generic form of the Lagrangian with generalized coordinates. And this whole process here, I'll show you in a minute, but we actually already did a simple case of that. And so my example of this, because yeah, you're not going to fret over this formula here, okay? I'll show you how this always comes out. So the example was the plane polars x1 equals r cos phi, y or x2 equals r sine of phi. Remember the kinetic energy, well actually, let me write make some room over here. So what we had was L was 1/2 m r dot squared plus 1/2 m r squared phi dot squared. I'm just going to write minus u of r and phi. So we already did this work once, right? Well, what is our 2x2 matrix for this situation here? It's not so much what's on this side, it's actually comparing these two things. And this should make it really apparent once we figure this out. Right, I'm saying we have a general quadratic form, it's complicated, 2x2 n by n matrix, generalized velocities. But here's the actual example we've done already. So how would we express that 2x2 matrix? If I say any more, I'll give it away. Anybody? I'll give you a hint in blue. The matrix elements, this is 1/2, are this and this. They're on the diagonal, that's right. So what about the values of the off diagonals? The off diagonals are going to be 0. See, the off diagonals will be r dot phi dot terms, right? But we don't have any mixed terms. So these are 0. And this one here is m. And this one is mr squared. And as advertised, they are functions of the coordinates, fundamentally, right? This one doesn't have a coordinate, this one has a coordinate. So yeah, when you do it in an explicit case, you just work your way through it and line it up and you'll be fine. So as a good homework problem, very important one actually, would be to construct the Lagrangian for a point particle in spherical polar coordinates. Construct L equals T minus U for point particle in spherical polar coordinates. So you're going to have a little bit more work to do Because remember, you've got x equals r, I'm just gonna write one down. Sine theta goes phi. X dot equals, right, y dot and z dot. X dot, y dot. So then, yeah, then you have to do x dot, y dot, and z dot. And remember, you got all that chain rule going on. You square them and sum them, and you get a bunch of sine squared plus cosine squared equals 1 terms. And then you eventually get a Lagrangian. It'll actually start with half mr dot squared, and you'll have 2 more, right? They're all going to be diagonal. So the homework is to construct this here and write down this A, I, J, R, theta, and phi. It'll be a 3 by 3 matrix. 3 by 3 matrix. It's going to be easy because they're all diagonal. It's a little bit of work, but that should drive the whole point home. Because then you'll have this situation for spherical coordinates. Later on, when we do small oscillations, we will get systems with mixed derivatives, with off diagonals. That gets more interesting then. But for now, you're going to find a 3 by 3 diagonal matrix. So that'll be good. Did we already have anything for next week, or would this be the first one on next week's?
Hold on, this must be for next week.
This is for next week's one?
No.
This is for next week. Next week. We already drew a line under this week, right? I'm just wondering if we had anything new for next week, or is this the first one?
Yeah, this is one.
Good, perfect. Okay, so this is the condenser for all of this. This is actually the condenser, but when you do this, you'll see what's going on with this form, right? This form looks really complicated, but it's actually just what naturally happens. Okay, good. So we're constructing generalized coordinates. We've got that construction. You know, maybe I'll put one of these funny ones up on the board as well. I will. So here's another homework problem. I'll get started on this one. So this one I'll put as homework as well. This is a system we're going to work with a bit. The idea is this: we've got an x-axis, we've got a mass on a spring, capital M, K. And now we're going to attach that legendary pendulum to it and find its Lagrangian, construct this Lagrangian. So this thing is nicely described with the coordinate x. Just call this thing coordinate x and let it be at that. But then this one has to have a coordinate as well. In fact, I could say this, I'll give this one a capital X, and this one I'll give a lowercase x and y. The interesting thing about these is that the Lagrangian method is going to give you the simplest version of this, and it's not going to look simple at all. But we gotta work this out. So yeah, we've got a pendulum here, a rigid rod, it can swing back and forth, we've got a big mass on a spring. No friction. No friction. So here's the way we're going to do this. We're going to say T is equal to 1/2 capital M capital X dot squared plus 1/2 lowercase m lowercase not done when we do that. We're not done with it yet. And the potential energy, we can say is a half K capital X squared, just the mass on a spring, right? Plus mgy for that little mass. So this is actually a kinetic, this is potential, but if we subtract one from the other, it's not a Lagrangian, because x and y and capital X are not independent of each other. There are really only two independent variables, capital X and phi. So that's what we have to work our way through, and we'll do it really systematically. I'll just set this up. So yeah, we have this idea right here. Yeah, this one's also going to generate the cross term when we do small oscillation program. But here's what we have to do. We have to say little x is capital X plus L sine phi. You guys agree? What about little lowercase y? We can go with minus L cos phi. Now when you do this dot, careful with the chain rules, right? And this one dotted, and square them and add them up. So if you actually take x dot and y dot carefully, square them and sum, put them in there, you're going to get the form that we were looking for. Okay. You're going to end up with x and phi only. So this is your homework assignment. I've set it up. Always take it from the top when you turn this in, right? And then start doing the chain. Well, I'll even give you one example. So
What
this
variable are we taking this derivative with respect to?
the dots.
Yeah.
These are total time derivatives. So for example, x dot is equal to capital X dot plus L cos phi dot. Right? Chain rule. Sum and square and sum. So when you've done that, then you have your L equals L of capital X and phi. After you've done that. And then it really is Lagrangian. You could have the equations of motion. I'll even write it here. So your equations of motion will be d over dt dl d capital X dot minus dl d capital X equals 0. Then you'll have d over dt dl phi dot minus partial L respect to phi equals 0. It will be a mess too. Those equations of motion are pretty involved. But yeah, so the task is homework, so construct L. And the other thing will be, and the matrix, I'll just call it Aij of X and phi. It's going to be a 2 by 2 matrix. Equals 2 by 2 matrix. So we'll do that, we'll hold on to it, and then we'll keep running with it when we start doing small oscillation. This one's going to have the cross terms, right? It's going to have the 2 by 2 matrix, cross terms in it, and we're going to learn techniques for solving these things. So this is a good one. We got a minute or two left. So now we have 2 good homework problems for next week. Let's wait till you know what we get. Okay, good. And I've even gotten us started. If you just very faithfully do all these steps, it's going to come out. In fact, the result is going to look like this. It's going to be 1/2 A, I'll go to X, capital X dot actually, I'm glad I brought this up. B, X, those are just subscripts like I and J. B dot, X dot plus 1/2 A B dot squared minus U of X. That's what I mean by there being a 2 by 2 matrix. It's going to have all the cross terms, and the important note that I didn't mention yet, it's always possible to make that matrix symmetric. So construct this A sub ij so that Aj equals Aij. So that the off diagonals are always symmetric. And what happens is it looks like you only have this term when you're doing the construction, and then you just divide it in half and place one here and one there. That's for useful theoretical reasons. Doesn't change the equation of motion. But yeah, that's this problem here, done systematically. All kinds of interesting stuff lurking in here. Did I bring the double pendulum video to class last semester?
You brought the actual level.
I brought it, okay, I brought the actual double pendulum. So Joseph White did some simulations. He put these differential equations and did simulations, and it looked pretty amazing too. They're smoother than the actual one that we have in the lab right there. I'll bring those to class sometime too. Okay, we've got a few minutes to see where we're time to wrap this up. So we have these two good problems. Good, so can I erase this? Yeah. So let's just wrap this up with a discussion of what we now have so far. I wrote these down. We'll decide later if we want to put them on the homework or not. The main thing is to get the Lagrangian and find that A sub ij matrix. Let me show you what we now have. So our Lagrangian mechanics now consists of, first of all, you've got a mechanical system that you're contemplating. Second of all, we have to choose the useful set of generalized coordinates. Choose generalized coordinates. Let's say the set of q sub I, right? They have to be independent, and they have to make it possible to solve them. A good example is if you're trying to do the central force problem with x and y, Cartesian coordinates, you're not going to be able to solve it. To this day, you wouldn't be able to solve it. You can put it on a computer, but you can't solve it analytically. So the choice of generalized coordinates is very important for Kepler-Codd, who chose plane polars. Then you have to construct L. So construct L is equal to T minus U in those generalized coordinates. So that's what we have up there for the homework. Having done that, we have equations of motion. And they just have this format. Yielding Qi dot minus partial L equals 0, I equals 1 to n. And of course now we have to figure out ways to solve those equations. We're not going to solve themselves. But that's where we are thus far. One more thing we actually have. We have if L is not explicitly a function of time, for us that's pretty much always going to be the case, then sum over dl dqi dot times qi dot, subtract off the L is equal to a constant. It's going to be a conservation law. This comes, and then I'll do this next time. This comes from the thing we did with the variation calculus earlier. Euler. This comes from Euler's second form. We did Euler's second form in this class. Yeah. This comes from Euler's second form. So we will. This is what we can start with on Friday. If we have time after all your guys' homework problems. So we got plenty to do. Okay, great. We're right in the thick of it now. And Friday we'll get caught up with the homework. And that's all I've got for you.